Welcome, this is Wireless Future. I'm Erik Larsson. I'm here as always with my colleague Emil Björnsson. Hello, Emil.
Hello, Erik. It's been a long time since we were talking.
It's been a long time, Emil. So how does it feel to be back recording?
It's great. So I had to bring up my green screen again and my microphone so I could speak with you and paste this whole thing together into an episode where it looks like we are at the same place, but we're actually in cities 2 hours away from each other.
Wow, yeah. So, I mean, a lot has happened since last time we were recording, in fact. I mean, there is, of course, the ongoing AI revolution. Can we even be sure that this podcast is for real and that it's you and me talking and just not some AI script that's read your books and then created the podcast?
Right, yeah. People should keep an eye on how many fingers each one of us is having during this video.
Yeah, 1, 2, 3, 4, 5, 6. Nah, all right. So what happened in the wireless community, Emil, since last time? It's been more than half a year, I think. Is there anything new and hot or anything that's been happening in the standardization that'd be worthwhile to talk about?
Well, I think in general, 6G is really happening now that there is the standardization work beginning and some first decisions have been made in 3GPP. Maybe not about new features, but rather about what to not really change. For example, they have decided to use OFDM and continue focusing on many other features that are already there in 5G.
Right, so that sounds like an interesting thing. Maybe something we should return to at some point with OFDM and all these other waveforms. But I guess the plan for today was to talk about another technology that's been discussed a lot, at least within academia in the last maybe 5 or even years or even a decade, namely reflecting intelligent surfaces, RIS for short. Okay.
Yes.
I think we actually have talked, you and me, on the podcast about that. And also when the podcast was in its very infancy in 2020. So what has happened since then?
Right. A lot of things has happened. So I think around that time, when we were speaking about it the last time, it still had many different names. I think now RIS has been the abbreviation that everyone is using, but it can mean a little bit different things. I think you said reflecting. Some people let the R mean reconfigurable. Before it was also intelligent reflecting surfaces. So there are many different terms for the same thing, but now everyone calls it RIS. But yeah, a lot of things has definitely happened, but it's still the same main thing of having a surface that behaves like a intelligent mirror that can sort of take radio waves that hits it and decide on how to reflect it, either as a beam in a particular direction or scatter it to a pattern that you want. And this is basically something that can assist communication systems in one way or the other.
Right, assist by creating additional propagation paths, right? I mean, that's the idea, so that it would kind of bounce the signal off or reflect the signal to create like an additional, presumably strong path from the transmitter to the receiver, then boost the signal to noise ratio or even create an additional rank component in the channel so that more data can be multiplexed. So what has happened? Because these ideas have been around for some time now, and what has really happened in the last 5 years with this technology?
Right, so I think I came across it in the autumn of 2018 when I was reading up for writing a magazine paper, and then I think it really took up in 2019, and we were talking about this in 2020. Then it was already in the hype going up, and I think now we have probably passed the hype. And what has people produced? Well, there have been a lot of works within the communication community, studying how you can add RAS to all kinds of systems. And of course, you do better if you just configure them perfectly, then things would be better than if they were not there at all in the system. Then people have developed all kinds of signal processing algorithms. And finally, there's been a lot of hardware design. So actually, this kind of surfaces that can reflect signals in controllable manners have been studied for decades in the antenna and propagation community. And now they have been developing prototypes of different kinds, and there are even companies that are selling prototypes that you can buy if you want to test things in your own lab.
So you're saying there are like off-the-shelf prototypes or products that you could even buy and just for fun to play with in the lab or to actually deploy in the field?
Yes, exactly. So I actually have one of those here next to me that I was buying from a Taiwanese company, TMITech, a year ago.
Cool. Huh. So what is it capable of? What does it look like?
Right. So this is a square shaped array. So the outer box is like 28 by 28 centimeters. So it's not that big. But at the inside, there is like an array of 18 by 18 centimeters, which contains small controllable elements that reflect signals. So this particular product that I have is from the 28 gigahertz, so millimeter wave band. Well, I can also buy them for 4 or 5 gigahertz. That is more like a Wi-Fi band. And what you can do here is that you have 32 by 32 controllable elements. So that is 1024 elements in total. Each one of them will reflect the signal, but you can switch between 2 different phase shifts or delays of the signals.
So individually for each one of these little atoms, you can switch to phase. You said in 2 different positions, so like plus and minus.
Yeah, so presumably like 0 and 180 degree or whatever other 180 degree separation. And on the back side here I have a control unit that you hook up to your computer, and then you can choose what kind of phase shift pattern you want in order to control how the signal is going to be reflected.
Oh wow, I mean, it sounds like a humongous number of combinations that this surface could be reconfigured. And if you got like 1024, you said, atoms, then there would be like the power of 2 to 1024, which is like almost in like infinity. So that'd be really a tough task to search through and optimize all these combinations, I can suppose.
Exactly, but the software to this one is simplifying the life, because it presumes that you want the signal to go or arrive from one angle and leave to another angle. And it comes from different distances there, and then you type in, this is my location of the transmitter, this is the location to the receiver, assuming a line of sight scenario, and then you just calculate what phase shift pattern you want.
Oh, so you're saying that you basically you're configuring the surface for some specific incidence and reflection angle, and then you will compute the weights of these atoms in software, and that's basically how you configure it.
Yeah, exactly. And
yeah, but I mean, would that work if you don't? Or it sounds like, I mean, you would need line of sight propagation for that to function. Is that so? Or would it also work if you don't have line of sight?
Yes, for this basic feature, you primarily want it to be line of sight, or at least the signal arrives from one main angle and you want it to leave from one main angle. It might be that there are some other reflecting objects in those specific angles, but yeah, this is specifically for line of sight, or creating what is known as a virtual line of sight, where the signal sort of is coming in line of sight to the surface, going in line of sight towards the receiver, but maybe the transmitter and receiver doesn't see each other, and you want to go around an obstacle, for example.
I see. So yeah, I heard that term before. It's a virtual line of sight. So you're saying that means that you basically don't have line of sight, but you have a reflecting intelligent surface somewhere, and you got line of sight to the surface and line of sight from the surface, and then it kind of reflects there, and you pretend that this path with reflection is like a line of sight.
Yeah, exactly. So from that viewpoint, if you want to deploy this in the real world, the idea is that you have a base station at a fixed location, and you deploy this RAS also at a fixed location, and there you can already make sure that they see each other in your deployment phase. But then the receivers might be at multiple fixed locations that you want to switch between, or they can move around, and therefore you want to change where you are reflecting the signal so you are reaching the users.
Right, sure. So this little product that you got on your desk, would that be capable then of reconfiguring itself when the mobile maybe moves around, for example, or would you have to like redo the software every time? How does that work?
Right. So so far in my own experiments, I only use this more at the slow pace, where you connect it with an Ethernet cable and you're controlling it with your with keyboard yourself.
Oh.
But there is a cable that you can connect as well, that you can use together with some kind of real-time algorithm. And I've seen other people in labs doing that, and then you can basically estimate where a user is and feed it in there. But of course, that estimation is also a challenge on its own.
No, sure, yeah. Oh, I'd be curious to know more about his hardware, in fact. But what are these RES gadgets going to be used for? I mean, what are like the prime use cases or killer applications for them that have emerged now after all these years of research?
Right, so we wrote a paper recently called Reconfigurable Intelligent Surfaces in Upper Midband 6G Networks, Gain or Pain.
Gain or pain or gain? So
yes,
what is it?
Exactly.
So the upper midband is like millimeter wave, or what is the upper midband?
That's actually the range between what we are using today in the 3.5 gigahertz band. So basically from 7 up to 28 or 24, that is what is called the upper midband, and that is what people targeting particularly to build new systems there. So if you build a new system, you also could have the opportunity to plan from the beginning to deploy RS.
Right, so from 7 to 28. I mean, it sounds like it is primarily a technology for higher frequencies, but it also, to my understanding, millimeter wave access, for example, was never so successful in 5G. So maybe could it be used also for lower frequencies, or would it just become too big and heavy? Or how is that? I mean, how is it that this is the band that you studied in your paper specifically?
So the main reason that we studied it in this paper was that this is just what people are interested in, deploying new network in that band. And but I think in principle you can deploy these surfaces in any frequency bands, but there is a lot of indications that you are benefiting the most from RES as compared to other ways of providing better coverage when you go up in frequency, particularly because we know that the higher up in frequency you are, the more the coverage becomes kind of binary, that either you are in coverage or you are blocked by big objects, and then an RES can make a huge difference.
Right, I can see that, because as you go up in frequency, propagation becomes more like less scattering maybe, and more like optical rays that either make it through or don't, or get reflected somewhere. So what are the use cases that you in your paper have studied and simulated and discussed, Emil?
So we studied 4 particular use cases that we think are relevant for the future, and it could be relevant for more than just one carrier frequency, but the first one is fixed wireless access, which is a use case that we didn't really have before 4G, but it turned out to be one of the important new use cases in 5G. Even if people were talking about many other things in 5G, this is actually one that on some markets where we don't have so much fiber penetrations to people's homes, fixed wireless access became an important thing.
Fixed wireless access. Wow. So at in this band from 7 to 28 gigahertz.
Yeah, in principle, but it could be any band where you would like to provide it. So this is a scenario where instead of digging a fiber cable to someone's home, you would like to deliver similar performance wirelessly, and then you can put out an antenna at the home of a user. And then from a base station site, you would like to provide coverage to as many homes as possible, so that you can reach a critical number, so this investment in more infrastructure would be better. And then the idea would be that if you put out some RES, well, then you can extend your coverage at this base station and cover another bunch of different homes.
I see. But where would the RES be installed? Would it be close to the home where you got like the customer's antenna, or would it be closer to the base station, or would it be somewhere in the middle of between the two?
Right, so mathematically, if one would like to get the best signal to noise ratio, and if you have the liberty of picking anywhere, well, then it should either be close to the transmitter or close to the receiver. I could imagine that in order to get many different customers here, you would like to find a place that is maybe a valley or something like that you can see the top of this valley from your base station. You put an RAS there, and then you let the RAS sort of reflect the signal down towards different houses and switch between them quickly, so that you can provide and divide your capacity between these different homes.
Oh, so when you say switch between them, you really mean like switching over time, so that these users are time multiplexed, and whoever gets favored by the reset at the very specific moment will get a boost in his SNR and data rate.
Yes, exactly.
So that use case, in fact, I never thought about that use case before, but I guess in fixed access, this is implied by the name more or less, then the customer antenna and the base station will be stationary, so you'd only have a few small reflections from objects around that might be moving, but at high carrier frequencies, those might not contribute a lot, so the channel will be static over a long time, and then it should be comparatively easy to configure the res. I mean, you could tell it more or less the angle of incidence and the angle of reflection that you desire, and then just the time switching pattern, I suppose, and that would work.
Yeah, exactly. So that also comes into them, that the algorithms are important to be tuned to the particular propagation scenario that you're having. In this case, it is line of sight, it is something that varies slowly, so we can design for that. And then it is an important thing that a surface like this can basically only take a signal from one direction and reflect it in one direction, or at least it can only have one reflection pattern over its entire frequency range at the same time. And that is why you need to time multiplex users rather than split them in frequency or send multiple beams to the user at the same time. Well, through an RAS you can only provide like one beam, but there can be other scenarios where you already have some paths directly to users, and then when you throw in the RAS you get an additional one that can help you distinguish between the users.
Right. So what other use cases do you foresee for these?
Right. So what we really saw in the simulation when it comes to this fixed wireless access is that the biggest gains comes in scenarios where you create this kind of virtual line of sight path that we talked about earlier. So you need to have line of sight to the surface, and you want to have line of sight from the RS to the different homes. And one can imagine other scenarios where this will happen. Some situation where you would like to enhance capacity within the cell in particular regions. So for example, you could have a situation where you are covering nicely the streets in an area, but you then would like the signals to go into some other streets, or you have some big blocking object somewhere, and you want to reflect into those areas that those objects are blocking. But now, instead of having fixed locations, you have users that moves around in these areas, and therefore you want to more dynamically change the RS configuration so you can follow those users.
Well, now you're talking about mobile access, so now we might have like the customer here might be a cell phone or something that's moving around potentially quite fast in the cell then, no?
Yeah, definitely.
And then of course there will be a challenge in how to reconfigure in real time all these weights that you talked about earlier.
Yes, exactly. So this is definitely going to be an issue. The interesting thing when it comes to this is that we once again discovered that the choice of propagation scenario makes a huge difference. First of all, the RAS is making the biggest difference when you have line of sight to and from it. So you are helping mainly users that can see the RAS as well, even if they're moving around. And that is helping you a lot when it comes to actually doing the configuration. Because if you design a smart estimation algorithm, you can then narrow down the scenario to, okay, I know physically where my base station is, I know what the RS is. What I like to estimate is sort of the angle and maybe the distance from the RAS to the user. And that is just 2 free parameters as compared to, you have 1024 elements inside the RAS I have next to me. So you can reduce everything from 1,000 to 2 free parameters to estimate, which is much easier in principle.
I see. I mean, it sounds a bit like channel estimation in any MIMO system, where, of course, if you know that you're in line of sight or you're in far field line of sight, then it would be enough to estimate the angle or possibly, elevation and azimuth. But in any case, just a few parameters as opposed to estimating thousands of coefficients. So how large are the gains then? I mean, what would we expect to see if we were to deploy a RIS in a cellular system with mobile users? And let's say that we got a large bandwidth, because we typically do, right? Could be 20 megahertz, could be even, I suppose, up to 100 megahertz or so. Don't these users already get all the capacity they need, or how much could the RIS provide additionally?
Right. So this becomes very scenario dependent, but in our simulations here, we assumed 100 megahertz of spectrum, and then we had a range of performance from 4 to 10 bits per second per hertz for the users, and we could add 1 to 2 additional bits per second per hertz per user in this situation. So relatively you could get some 50% extra, or you can just say that every user can get a few hundred megabit per second extra. No, probably users don't need all of that extra capacity, but the system at itself might need it when you have a lot of users that you would like to switch between, and so you can more enhance the capacity of your system rather than maybe boost the performance for everyone. But there will be some use at the edge of the cell that definitely benefit, and it goes from really no performance to decent performance.
I can imagine. I mean, it's always covering the cell edge that's difficult in wireless comms, right? And also, cell edge is not to be necessarily taken literally that you're far from the base station. It could be that you are really in an unfavorable situation where you're blocked by some objects, you're deep in the basement or somewhere, or even that you, for some reason, you might not be very far away again from the base station, where you could have a very poor channel to the base station and a much stronger channel even to an interfering to the next door other cell. And I suppose it's in those situations where you could really boost the signal to noise ratio, and where the RIS could potentially help. And that would be valuable, because that's really the scenario that's difficult to cover with standard technology. So are there other situations, where you could expect even larger gains?
Maybe not larger gains specifically, but you could imagine that there are particular regions in the cells as well. Like there's a park where you have a lot of users, or a neighboring street or something like that, where you like to provide better coverage. But one thing that we really saw was that in a lot of the academic work that are studying RAS, they say, the only way of reaching a user is through the RAS. And there is no path directly between the transmitter and the receiver. It's totally blocked.
Hey, wait. I'm not getting it. So there's always a path directly between the transmitter and the receiver, isn't there? It might be weak, but it's always going to be there. No?
Yes, exactly. That is the point that we were seeing very clearly. People are often saying that it's very weak, so therefore we can neglect it. But we see that it actually in the upper midband plays a huge difference. So if one is neglecting that path, everything will be wrong in the simulations. That was something we noticed. But it then also puts the finger on that what kind of static path between transmitter and receiver would we expect in reality? Well, maybe in this are scenarios where the signal needs to go through the building or bounce on a lot of objects before it reaches the receiver. And if we then go up in frequency, 2 millimeter waves, for example, as the RAS I have here, well then, relatively speaking, those paths typically becomes much weaker. So we can also imagine that RAS becomes more attractive the higher we go up in frequency, not because the reflection as such becomes much different, but because these static paths that will be there, even if the RAS is not there, they becomes much smaller.
Oh, because the static paths become smaller. I see. No, interesting. Sure.
So what one can potentially argue that RAS is mostly useful in situation where you are at millimeter waves or even higher frequencies, because then each base station has a very limited coverage. And if you, one argument people are having sometimes that if you have bad coverage, just put up another base station. But if you put up that one, well, then you would have yet another place where you have limited coverage as well, as compared to putting up at lower frequency where you can get 360-degree coverage from one base station. So a few RAS might make a much bigger difference at higher frequencies than it would do at lower frequencies.
So how easy would it be to put this up in practice? I mean, they would need to be installed, I suppose. They would need power. They would need they won't need any backhaul, no, but it would need a power supply, and presumably some sort of control signaling would be through the air. So all they need is a power supply and somewhere to sit on a wall or somewhere.
Yes.
So I mean, it sounds like that would be a lot easier to and cheaper to install than putting an extra access point there, even outdoors. Is that accurate to say?
Yes, this has been the vision all the time, and I think it seems to be true. But yeah, one needs the power supply. I think this prototype here consumes some 20-30 watts, but if you really build it to be more lean, then it could be substantially less than that. But yeah, some power supply you would need for this. You need to figure out how to deploy it maybe on a wall or something like this, and how to rotate it, because just as any other RF hardware, you want it to look big and rotate it so that the angle that it reaches it are not too high as compared to the
Yeah, I mean 20 watts is still substantial, but if you could build it, as you said, leaner, maybe it could consume like a handful of watt or so. It could even be solar powered. So they probably a case they could be made for that, but at the same time it's a little difficult to see how we could be competitive to network controlled repeater, which is a lot simpler to build and presumably cheaper and also more power efficient. But that's another story. Okay.
Yeah. And I think it's the control unit here that consumes most of it, because I was also part in one of the papers that demonstrated outdoor RAS usage at the early years of this technology. And there, I think the RAS as such was consuming less than a watt, but the control unit consumed most of it. And that was just because it wasn't optimized for.
Oh, really? Because it wasn't optimized. I can imagine. Yeah, sure. All right. So we talked earlier about the challenge to configure all these atoms, and you had in your prototype, you had 1,024 of them. So each one needs to be configured with a phase shift and with a discrete phase shift. I think you said it was like binary, so it's basically like plus minus one. But to me, this is the real challenge in making RIS operational and efficient, how to actually estimate channel state information in real time, and based upon this channel state information, compute how these weights should be set, and then also communicate that information instantly to the RIS. So won't this be a big challenge? And particularly, I mean, if you're at the cell edge, then you're going to have a weak signal, and the control channel will also be weak, presumably. At least if that control channel is sent within the same band. I'm not sure. I mean, maybe it could be sent out of band or through some other means, or who knows, through a cable maybe. But my understanding has been that some of this control signaling at least would happen within the band. So won't that be a huge challenge to pull off?
Yeah, and I think it is something that remains to be fully demonstrated in the real world. In theory, the problem would be that if there is no structure at all in the channels, you have 1,024, in this case, entries to estimate, and you would have to sort of send signals at least 1024 times in order to observe all the different parameters and estimate them, and that will take a lot of time, and maybe the channel will have changed. And when we worked on similar kind of problems in MIMO communications, then you want the base station to actually be able to cover any part of the world. So therefore, you need to solve that most challenging problem somehow. But when it comes to the RAS, if we narrow down the use cases to this kind of virtual line of sight situations where you only want to estimate angles, well, then you can at least simplify your algorithms. And then you mainly have this issue with the SNR that you mentioned. For example, what a lot of the algorithms are suggesting is that you let the user send the known signal a few times. The RAS is changing its configuration between some predefined ones in order to estimate or observe the channel different ways. Then you have an algorithm that tries to predict what was the angles, calculating what configuration you should have, and then you can do that calculation at the base stations, and you can let the base station tell the RAS.
No, but that makes sense. I mean, basically you would be exploiting structure or sparsity even in the propagation environment, so that you don't have to try all possible combinations, but just to select few. And based upon that, perform some inference on what the channel looks like, and then based on that inference, compute how the weights should be set. But it still sounds like in a way, a technology that scales poorly. I mean, if you were to go from like 100 to 1,000 to 10,000 or a million or something atoms in the RES, you would need correspondingly more signaling, presumably. Because it's also that the more atoms you put there, the higher would be your expectations on the utility of the RES, and specifically on the increase in SNR and power boost that it would give. And the higher you go in SNR, the more scattering points you're likely to discover, so that your model starts breaking apart. I mean, if you're at low SNR, you could say there's only line of sight. You go up a bit in the SNR, you discover there's actually a reflected path on top. You go up a little further, you discover that, oh no, there are like another 10 reflections or scattering points that we also have to consider. So it isn't obvious to me that it scales very well, but of course that remains to be seen in all these practical use cases that we got.
Yeah, and even if you have more than one path, if you are in a situation where one of them dominates the potential of the others, you can try to ignore the weaker paths and just focus on reflecting the signal from the strongest path towards your receiver. Of course, you then throw away something when it comes to all the signal power coming from these other weaker paths, but at least you can bring down the complexity of your estimation algorithms.
That is totally true. I mean, what I meant is that if you discover additional scattering points or propagation paths, then in principle those could be exploited also to improve the rank of the channel potentially, and it just isn't obvious how the scaling behavior would look like here. So now this little prototype that you got on your desk, have you been able to configure that in reality yourself and actually see any gains?
Yes, definitely. So we have done 2 different measurements. One of them, one can find a video on YouTube about, and one is a technical paper that I have been submitting to a conference. So in the first case, we just wanted to demonstrate this ability of creating a virtual line of sight path. So we put out the transmitter in one angle and the receiver in another angle. And since I don't have an implementation of any advanced estimation algorithm, we had to measure the angles more with laser pointers and other kind of visual means. One of the tricks we did was that we had a transmitter that was very directive, and we put it in front of the receiver, which was more omnidirectional, so that the signal were naturally not going to go directly from transmitter to receiver. And then we sent the signal to the RAS. We were able to reflect it towards the receiver as well, and it all worked as it was supposed to be. We were able to have a signal coming from, say, 10 degrees, and we reflected towards 15, 20 degrees in the other direction. So that all works. what we noticed were that, yes, there could also be other objects. So in the first measurement, we put a laptop next to the receiver, and we realized that a laptop cover was actually reflecting the signal towards the receiver as well. So
I can imagine. I mean, of course, you could do whatever you can do with the Reese. It reconfigures so slowly. You could basically do with a passive emitter, like a metallic plate or something. Even your laptop screen would do it. I mean,
right. But one of the challenges there was that I first told my team that let's try to reflect the signal around the corner, because the specification of this RIS is saying that you should be able to handle angles up to 60 degrees in one direction and 60 degrees in the other direction. But as soon as we were above, say, 40 degrees on either side, then it started to not entirely work so easily as we were expecting. I mean, sometimes we get a strong signal, sometimes we didn't, but at least the beam pattern were not at all as we were expecting them to be. We didn't really figure it out, but that at least keep me thinking about that. One of the use cases is that you would like signals to be reflected around the corner, and then you need the total angle range from one direction to the other one to be at least 90 degrees. And with this RIS, I'm a little bit skeptical how strong gains you will actually get in those scenarios.
Right, but that's quite interesting. I mean, it would be interesting to know whether that's a fundamental limitation of the technology, or whether it's just because of the software that goes into that gadget that you got on your desk.
It probably has something to do with the element pattern as well. So an antenna always have a particular gain pattern, and you want it to be wide enough.
Sure, of course. I mean, it's all interplay between how the actual atoms look like and how they are configured. And I suppose there's also going to be a loss associated with this binary quantization of the phase angle that one could analyze. I'm sure that has been analyzed.
Yes, definitely. And this kind of just reflecting an angle is something that people have been doing for several years. So that wasn't a new thing as such. But what we did next was more of a novel experiment, to my understanding, because we realized that there is something called the Fraunhofer distance, which is telling you at what distance from a radiator can you see the spherical shapes of the curves. And for this RIS, it's roughly 10 meters. And when you are at much shorter reception distances, you can do things like beam focusing, where your signal is not only steered in a particular angle, but also in a particular distance range where you get the signal that is strong. So that we did an experiment. We put the receiver at roughly 1 meter distance. And then in the software, we can not only control the angle, but also the focal point.
Also the focal point.
Yeah, so we move the focal point in the direction towards the receiver. And we started at 0.5 meter, went up to 1 meter, we saw how the signal goes up, and then we continued moving it further, and we saw then how the signal goes down again. And that creates this kind of focusing behavior that one would be expecting from beam focusing.
Sure, but that's pretty cool. I mean, it sounds like you're actually able to obtain some beamforming gains for real using this little toy.
Yes, exactly. And I can just comment on one more thing there. So it turned out that if you go with mathematical formulas for how the shape of that beam focusing would look like, it matches nicely with this kind of what we measured, and also this bit resolution that you were saying, that every element only have one out of two different phase shifts. That reduces the gain by a few dB, but it doesn't change the sort of shape of this beam focusing. So we're also there able to develop mathematical algorithm that matches with the experiments.
But that makes sense. I mean, that's what I kind of expect, I think, that you get that sort of effect. Interesting. So, but now, given that you have actually in your lab been able to demonstrate beamforming gains, and given what you have analyzed in your papers about all these use cases and the potential gains there, that actually seemed quite substantial. I think you mentioned 1 bit or something of increase in spectral efficiency. Did you say that? Then how is it that Reese was or that Reese is no longer considered as a technology for 6G?
Right. I think that this has a lot to do with the frequency range of interest. So as we were talking about earlier, it seems like the biggest gains for these surfaces in reality comes when the frequency is substantially higher than the system of today. We should probably be at millimeter waves at like 28 gigahertz as this surface has, or larger, to really see big gains. And that is not where the industry is going for the moment. So they tried with millimeter waves in 5G and standardized and built hardware, and then it turned out that it was only in the US where it was taking off, and even there the deployments have stalled a lot. So it seems that until there will be a new wave of millimeter wave deployments, maybe in a different way than these outdoor systems that they try to build, it's not until millimeter wave takes off that having these RAS as an add-on would also make a lot of sense. So I think that is the reason why 3GPP have sort of paused the attempts of standardizing something like this and focus on other things that seems to be more urgent.
Sure. I mean, it sounds like RIS would be mainly or mostly useful in high frequency bands, and even that the higher is the frequency band, the more useful it could potentially be. So how about terahertz then? Because if now RIS could be useful at millimeter wave, I think you mentioned earlier 28 gigahertz, then what about if we go up to sub-terahertz band? Would RIS not be potentially very useful there?
Yes, so the people who have been building this kind of so-called meta surfaces, materials with properties that you can control so they reflect signals in controllable manners, they have been considering all kinds of frequency ranges over the years. So it's just the implementation aspects that becomes a difference. So if you go up towards terahertz frequencies, you might not use this kind of lumps electronics implementation that we have here, but you might use graphene, or you might use some semiconductor materials where you have other ways of controlling it. So yeah, in a surface like this, you typically have some kind of varactor or pin diode that is changing the voltages inside its element, and that determines the reflecting properties through its impedance. And you will need other materials and other control mechanisms when you go up in frequency, and of course each element also shrinks in size. But there are ways of doing this for terahertz for optical ranges, for example.
Interesting. So that'll be an exciting development to follow in the future if RIS are also developed for the terahertz band, because they really have this problem of blocking. I mean, you basically got either you got line of sight or you got nothing. So you have to create. I mean, you could have a reflected path with some luck, but it would really help to be able to create this virtual line of sight that you spoke about earlier.
Yeah. And if I should pick up on another thing you said recently, we had an episode a few times ago about network control repeaters, which is another way of amplifying the signal between transmitter and receiver. And if you are using such repeaters at lower frequencies, then it's probably enough to have one receive antenna, one transmit antenna. But if you go up towards millimeter wave systems or higher, you will need an array of antennas where you also need to know from what angle did the signal come and towards what angle do you want the signal to come. And then they have started implementing such things and standardize such code books of angles as well. But when you go into the whole angle business, then treating RAS in the same frameworks becomes of interest as well. It's kind of similar things, but it's like you need something bigger, so you need to amplify less with power amplifiers, but then it becomes much more similar. But once again, we are not using millimeter wave or terahertz system for the moment, so maybe that is why the development is stalled in the industry.
No, sure. I mean, at lower frequencies, it seems to be that network control repeaters are much more feasible, simpler to build, simpler to operate. They can be sharply band selective, which is likely to be a stringent requirement for any technology of this sort to be deployed in practice. But as you said, I mean, if we go up very high in carrier frequency, then you might need an antenna array at the repeater. And then we are basically in the in a way we're back at the the challenges that we have with the RIS. Okay, so now there also seem to be a lot of other related technology that builds upon the basic RIS concept and which is being developed. There's this notion of active RIS and star RIS and beyond diagonal RIS. Could you speak to some of those and how they potentially could change the game?
So if we take an active RIS to start with, that is not too different from what we call the network control repeater. So in that case, each element here would have a small power amplifier next to it, so you can amplify the signal before reflecting it, and that makes the signal that is radiated stronger, but it also adds some transmitter noise, and that basically limits the SNR at the receiver side, but it could allow you to build smaller RIS, or it sort of takes the range between what we normally call network control repeaters and what we call RIS or passive RIS, and then it develops a range of things in between there that could be of practical use as well.
Sure. So you're saying that you get all the advantages of a repeater, but all the disadvantages of a RIS.
Yeah. So I think one needs to be really careful when it comes to comparing these type of things, because on paper you can develop technologies that appears to be better than everything else, because you get the benefit of both things. But to really properly model the bad sides of two different technologies and how they add together, I think that is important as well. So active RIS is not too different from traditional repeaters or relays.
So how about the beyond diagonal RIS?
Right, beyond diagonal RIS is something that has been studied a lot in the last few years in academia. I think the thing is that it takes much longer time for hardware engineers to build things than it takes for communication people who are only doing theory to develop things. So they sort of run out of problems to solve, and then they try to figure out new things, and then they imagine more advanced hardware implementation. So the weird thing is the name there, beyond diagonal, which is kind of saying that the RIS, like the one I have next to me, would be diagonal, and obviously it is square. But this refers to a mathematical property that if you say that there are signals arriving to each of my different elements here, and there are signals leaving each of these different elements, and the sort of transformation from a transmitted to receive signal, that is a diagonal matrix where each entry just shows the amplitude and the phase shift.
Is that really accurate? Because isn't there coupling between the atoms even in the standard RIS? I mean, the one would have to very carefully model in order to like really understand what's going on and really operate them optimally.
Yes, in practice it's definitely like that, and for that reason the manufacturer of my RIS is not actually publishing how they are doing the calculations, so they just take the input from what signal direction and distance you want to have a signal source and where you want it to go, and then it calculates something presumably compensating for this kind of coupling effects. But in theory, if you neglect coupling, then the reflection matrix that you are controlling is a diagonal matrix mathematically.
So the beyond diagonal is basically like enforcing or designing the RIS in such a way that there is more coupling between the atoms.
Yeah, you have some kind of controllable coupling, one can say, between them. So in principle, you can connect all the different elements together and have a way of sort of purposely leak signals between the different elements, so that what goes in one element can be reflected from a different element. And this creates a much more complicated mathematical structure. And it in practice it will probably be more expensive to build and create a lot of losses inside of the surface. But once again, if you neglect all of those implementation aspects, then you can do more because you have more control parameters.
Sure. I mean, but in the end, I mean, it seems to me that it's really these implementation aspects that will determine what's possible to do, because it sounds good that you could configure the coupling between the atoms, but how is that going to happen in practice? Would there have to be like a huge interconnection matrix or something with zillions of switches that need to be operated through digital control logic in some way? Okay, interesting. Let's see where that's heading.
Yes, so I've been spending some time trying to understand the potential benefits of that technology over the last 2 years. And because the first example I got was that someone showed that if you have a rich scattering environment between the transmitter and the receiver, and you put an RS there, then for a particular size, you can gain 60% in received signal power. And that sounds like a lot. Then once you remember that since the gain at the receiver grows with the number of elements squared, a conventional diagonal RIS that is 30% bigger would also provide a 60% larger gain. And we are not interested in rich scattering environment. That was one of the points I've been trying to make now for a while, that it is the case where you have a line of sight path to the transmitter and to the receiver where this shines the most. So what are the other benefits? Well, what you can do with a surface like this is that if you have multiple strong signals coming in from a collection of different angles, you can selectively reflect those ones in some other collection of angles. So yeah, you can basically do something more like multi-beam transmissions from this RS.
So that's the advantage of this beyond diagonal. You can actually reflect, like there would be two different waves that come with two different incidence angles, and each one could be processed and reflected in a different and unique way.
Yes, exactly.
Okay, yeah, but that makes sense then. That could maybe be a gain.
But let's not open the book about how do you estimate those channels, because that is way worse than it is for the normal cases, because there's so many more parameters.
I can imagine. Wow. So then there are also this other one is star RIS, simultaneously transmitting and receiving. Is that what it means? Star?
No, it's transmitting and reflecting.
Oh, transmitting and reflecting, that's what
exactly.
I meant. Yeah.
And transmitting is a little bit conceivable word, because for most people it sounds like you send something out from somewhere, but in this case transmission means that the wave propagates through an object. So this is like a surface where the signal can come in from one angle or from one side, and then you can control whether you want it to be reflected on the same side or go through the material and be reflected on the other side.
But that sounds like a cool thing. I mean, but then you want to mount it on a wall, I suppose, because there would be not much of a point to reflect it into the wall. It would be mounted somewhere like, I could be on like, well, it could be on a wall, but then it would be part of the wall, so that one side of the star is actually facing either side of that wall.
Yeah. So in principle, you could use it in an inner wall between two rooms where you don't need so much heat isolation, so a thin wall will be enough, and then you put out the surface. The signal can be reflected within the room where the transmitter is to provide better coverage there, but it can also go through the wall to the next room and be beam steered inside that particular room. That would be a particular use case for this. But to me, it also seems much harder to figure out where to deploy it while not getting other problems when you are making a hole in your wall and then you fill it with just a metasurface.
No, I mean, to me, it seems that the use cases for RIS are quite limited to start with, and for the star RIS, those are even more constrained. But let's see. Another one is this SIM RIS. SIM means stacked intelligent surface. Stacked intelligent metasurface. Is that accurate? Yes. Okay. So what is the SIM RIS? What is that?
Right. So this is maybe the latest things that researchers in this field have started to spend a lot of the time on. So the idea would be that if you have now this kind of RIS that takes a signal coming in from one side and reflects on the other side. It doesn't need to be simultaneously, but only so-called transmissive RIS. Signal comes in from one side, you control how it is going through on the other side. Then that whole operation is described by a matrix. that says how the signal is changed from the one side to the other side. And if you also view that kind of phase shift operation as some kind of non-linear function or so, then this looks very much like a layer in a neural network, for example, where you have some kind of matrix operation and then you have a nonlinearity. If you now stack multiple of these surfaces after each other, so signals go through one and it gets processed, then it goes through the next one, it gets processed, and so on. You basically create a computing machine where signals, radio waves, can be processed and change their shape, either to compute something, or it might be that one of them is like making a Fourier transform that transforms signals into beam angles or some other kind of operation.
Wow, but I mean, that sounds pretty cool. That sounds like something really exciting, I think, to look deeper into. So basically you would like perform computations via the wave propagation that happens within and in between of these different meta surfaces. And you said you could compute the spatial Fourier transform, which traditionally has been done through a Butler matrix microwave circuit, but could actually be done within this RIS itself. How mature is that technology? Are there already prototypes available, or are these just theoretical papers suggesting that it might be possible to build something of this sort?
To my understanding, it is mainly theoretical papers, but people have been starting to try to build this thing. And I was visiting a lab the other week where they were taking some transmissives they have built and tried to put them next to each other, and so far it didn't really behave as they were hoping it to be. But yeah, it's a work in progress. But I think one of the issues you will certainly get is that each surface, even if the signal is going through it and then it reaches next surface, there will be some back reflection, and then the signal will start to bounce back and forth inside of these different meta surfaces as well. So people are also in this academic papers assuming that basically the signal going from one layer to the next one is lossless. There's no loss in signal power, which you are going to have all the time. So you can see a lot of papers on conferences saying that if you just add more layers, everything gets better. But it won't be like that in practice. They will either you have to put amplifiers and then you accumulate noise, or you would get a weaker and weaker signal through it. So there will be a certain number of layers that is optimal.
Sure. I mean, to me, it sounds like to do any meaningful work on this topic at all, you'd really need to delve in and model very carefully all the electromagnetics, which seems like a tough call to do, or at least to obtain anything accurate and useful in closed form. It sounds to me like you would need full wave EM simulations to really understand how all these atoms would be interplaying. But let's see. Okay, so now it's been 5 years since you and me discussed RIS on the podcast. What is your prediction, Emil, for the next 5 years? Where will this technology stand in 2030? And which among these use cases do you envision that we will actually see where RIS has been deployed? How will the technology of Beyond Diagonal and STAR and SIM RIS evolve over the next 5 years?
Right.
Would you dare to make a prediction?
I can make some prediction.
Go ahead.
So I think 5 years ago, we had just finished a paper, you and me, together with one of our students, called Reconfigurable Intelligent Surfaces, 3 Myths and 2 Critical Questions. And 2 of those critical questions were, how can we really configure the RIS in real time? And what will be the actual good use case for this technology? And I think when it comes to the first estimation and control of the RIS, we have found some kind of solutions by now that you can do this. I'm not sure under how high mobility, but at decent mobility you can probably do something like this and exploit the fact that we narrow down the scope to line of sight to and from the RAS. But I think what we need to discover now over the next 5 years is really good use cases where this technology is paying off as compared to other technologies. And I think that there will be situations where you want to deploy just a reflecting surface that is not controllable, but that have a a shape.
So basically, like a metallic kind of plate, like a mirror, that you just send somebody up with a wrench to adjust so it points in the right direction. That's what you mean when you say
exactly. And the nice thing, if you build it with metamaterials instead of just like a blank metal surface, is that you can put it on the wall. You don't need to bend it, but and you don't need to rotate it. Instead, you compute in advance how you want the signal to be reflected, and that could be something that starts to be deployed in some buildings to provide decent coverage in specific scenarios. So I think that in local situations, to extend coverage in a factory or in a mine where you would like the signal to go into different tunnels, and the signal will not bounce very well on these rough walls, or maybe in some office environments, this is something that is going to be helpful. And if you are trying to build some kind of millimeter wave or terahertz links, particularly for like fronthaul or backhauling between different fixed points, I think this is the technology that an engineer will consider to deploy. So it will become mature enough so that you could buy something. There's a number of startups that try to fill the gap that is left when the big vendors are not really investing in this right now because the customer is not asking for it. So I think we've come to a stage where one can build this and deploy it, but the use cases will still be relatively narrow.
So, exciting times ahead. Thank you very much, Emil.
Thank you. Good to talk to you as always.
As always. And to the audience, see you next time.
See you.